Hello everyone, myself Dr. Sandeep. I'll be discussing today on the topic of artificial intelligence. More particularly, I'll be discussing what is called as agent and environment, and also we discuss various concepts like rational agent and how algorithms like search algorithms will help us in reaching the objectives of an agent. So first let's define what is an agent and an environment. Agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. So agent has two things. One is sensors which through which it perceives the environment, and it has actuators through which it acts upon the environment. So there are various types of agents, and uh, some of the examples of agents are a human agent. So we humans have sensors like eyes and ears, and we have actuators like hands and legs. So we pursue the world through eyes and ears, and we act upon the world through our hands and legs. Something like we move and we change the state of the environment. Okay, so we also have another example like a robotic agent, where the sensors are the cameras or infrared rangefinders or lidars or any other type of sensors, and we have actuators like motors. So through actuators it acts upon the environment. So this is a second example of an agent. So you can also pursue software also as an agent, where you send and receive the packets. Receiving is something similar to, somewhat closer to pursuing, and sending files or packets is somewhat closer to actuating or actuator. So these are some of the examples of agents, and so fundamentally agent relies on the percepts or the perception through sensors. So the list or the there is a term we use to depict what these agents pursue through sensors. They are called as percepts, and this sequence of percepts put together are called as percept sequences. And our agent behavior is nothing but mapping these percept sequences to some action. So for every percept sequence, if we have an action, then we are almost done. But what happens is tabulating all those percept sequences and the equivalent action can be somewhat tedious and large, and therefore it is not practically feasible. But what we implement, agent function is a theoretical thing, but what we implement is called as an agent program, which is how we relate these percept sequences to actions. So now let us come to an agent called as rational agent. So why are we interested in rational agent? Because we want to see, we feel that rational agent is the best way to realize intelligence in an agent. So our goal is to make sure that agent behaves intelligent, and one way of realizing an intelligent agent is through rationality. So through making an agent rational. So how do we define rational agent? So we have a sequence of actions which causes the environment to go through a sequence of states, and if this sequence is desirable, then the agent has performed well. So as we saw earlier, so we have percepts, and these percepts are related to actions through, and if these actions changes the environment in a desirable way, then we say that agent has performed well, and we can say that it is rational. But what is desirable and how do we quantify it? So here comes something called as a performance measure. So we need to maximize its performance measure. So that performance measure can be anything. Suppose like a robot want to move to a destination, and if it moves closer to the destination, maybe the performance measure gives a positive score. If it is go further, it gives a negative score. So a rational agent attempts to come up with a performance measure to quantify whether the sequence of steps taken is good in some sense. So that's how we define the rational agent. So some of the examples of rational agents we are going to see soon, and before we go there, we need to know what is called as task environment. So the task environment put together all the things what we have seen, which is to have performance measure, to have agents, actuators and sensors, and also the environment. So we call all these put together as PEAS, PEAS, performance, environment, sensors and actuators. And some of the examples of a piece, or you can take a taxi driver example, where your environment is road, traffic, police, pedestrians, customers, whereas actuators are steering, where you act upon, and sensors are cameras, radars, rangefinders, lidars, accelerometers, and you have a performance measure which says how safe you are driving and how fast you are driving, and how do you maximize the profits. All those things comes under the performance measure. So PEAS, performance, environment, actuators and sensors, put together called as the task environment. So these are some of the other examples of task environment. For example, if you take a medical diagnosis system, you have a different piece. If you take a satellite imaging analysis system, you have a different piece. So in this you have task environment, which put together all the necessary things of a rational agent. So now let us see some of the properties of the task environment. So there are various properties of task environment, and why do we need to study this task environment? It is important because you could either study a simpler version of a problem and slowly increase the complexities so that you can solve a much bigger problem. To know what is simpler and what is complex, you need to understand what all different properties you can say about the environment. And so when we discuss the search algorithm, those are applied for a particular case of these properties. As the complexity increases, the algorithms what we are going to discuss may not be applicable. So for what properties we are going to apply the search algorithm, we are going to discuss, but before that, let's see what are those properties and why is it important to study those properties. The first property is the fully observable versus partially observable. So I'll discuss the definitions of it. So you can have a situation where you can observe completely about the environment or partially. What is complete observing, and we'll see shortly. The environment can have a single agent or a multi-agent. It can be a deterministic or a non-deterministic. It can be episodic or a sequential. It can be static or a dynamic, and it can be a discrete or a continuous, and it can be a known or a unknown. So each of those are very important, and when we apply the search algorithms, we are going to apply for a one particular case of this task environment. So we can take the very simplest case and slowly see what happens if I introduce complexity, and see what all things are necessary to be taken care. So let's see first of all the definitions of each of these cases, and then we will go to a more particular case and apply the search algorithms. So first thing is the fully observable versus partially observable. So if an agent through its sensors is able to get the complete information regarding the environment, then we can say it is fully observable. If in case due to some noise and inaccurate sensors, if you are not able to completely pursue the environment, then you are saying that it is partially observable. So this is the first property, and your automated taxi cannot see what others drivers are thinking. So you cannot say it is fully observable. it can be said as a partially observable. So the second property is a single agent versus multi-agent, and this is very important to know because when we discuss various search algorithms, we have algorithms like adversarial search which works for only multi-agent, which are being designed for multi-agent, whereas all other algorithms like informed and uninformed search are designed for or can be applicable for the single agent case. So it's important to see what is a single agent and a multi-agent case. So for example, you take a crossword puzzle. Here it is a single agent environment. So you are playing to solve that puzzle. Whereas if you have a two agent scenario where, for example, like you have a chess, chess is a two agent, and it is not just two agent but it is also a competitive two agent, which means that each one wants to win the game, and a person's win is same as the other person's loss. So it's a competitive environment. There are other examples other than chess which are cooperative agents, for example like a taxi driver, where it is a cooperative environment. It is also a multi-agent, but it is a cooperative multi-agent environment. So we have other properties like deterministic versus non-deterministic, where deterministic indicates, generally deterministic indicates that it is not random in nature, it is not stochastic, which means that it is perfectly 100% without any uncertainty. So in technical terms, you can see here, if the next state of the environment is completely determined by the current state and the action executed by the agent. So if your next state is going to be determined by the current state and the action which is going to be executed by the agent, then we will say that it is deterministic. Otherwise it is non-deterministic. So what does non-deterministic mean? Which means that we cannot determine the state of the environment even though we know the current state and the action executed by the agent. Because of the many other factors, it becomes uncertain, and if that is the case, then we say it is non-deterministic. So deterministic is the simplest case, and if an environment, if there is an agent, and an agent need not worry if it is fully observable and deterministic, because there is no uncertainty. If it is fully observable, it means that you have observed the whole of the environment through the senses without losing any information. And if it is deterministic, which means that you can clearly determine the future based on the current state and the actions which it is going to be executed by the agent. Okay, so there is no chance for uncertainty. So usually we assume these cases that it is deterministic and it is fully observable. Only then we apply various types of algorithm. As and when we change the properties, the complexity increases and we need to follow different approaches. So the next, so the taxi driver case in the previous example, taxi driver is clearly a non-deterministic in the sense because one can never predict the behavior of the traffic exactly. So even though I have the current state and the action which I have taken, but I cannot predict the future because there are many random uncertain things. So that's a non-deterministic example. So what is episodic and sequential? So one of the best example of episodic is chess. So in chess, whatever we take, one of the best example of sequential is chess. In chess, the action, the step which I am going to take now is going to determine an effect in long term. So if there is an effect of current action on the future performance, then it is sequential. If it is not going to affect for the future, then we call it as episodic. So the agent's experience is divided into atomic episodes. In each episode, the agent receives a percept and then performs a single action. So it receives a percept. In episodic, an agent receives a percept and it performs an action. So there is no long term impact of it. Whereas in sequential, the current decision could affect all the future decisions. So chess or taxi driving are all sequential examples of sequential, and episodic is way simpler as compared to sequential. And then comes the static versus dynamic. This is pretty easier. If the environment is static, which means that it doesn't change, then we call it as a static environment. If you see chess or all those things, the rules, everything are fixed, there is no change. Whereas a taxi driver case where the environment changes, so it falls under the dynamic case. So chess can be treated as semi-dynamic when you are playing with a clock, but generally it is static because the environment is fixed, it doesn't change, we can predict how it is. So for example, the other best example of static is the crossword puzzles, because we know clearly what all states they are in. So each of those are different levels of complexity. So under each property we have a different levels of complexity, and we also have discrete versus continuous. For example, when we take the percepts through sensors, those can be a continuous data of along time or space. It could be discrete also. In chess it is discrete, but in taxi driving it is the percepts which receives through the sensors are continuous, and therefore it falls under the continuous case. And the final one, which is known versus unknown. So here the environment, in a known environment, the outcomes or outcome probabilities for all actions are given. So what are going to be the outcomes, or the outcome probabilities are all given. So we know something about what all possible outcomes are there, and if it is deterministic, we know perfectly the finite set of outcomes. If it is uncertain, so you also know, in a known environment, you know the probability of occurring a particular outcome. So if you doesn't know that probabilities, or if you doesn't know what all outcomes, list of all outcomes, then we say that the environment is unknown. So what is the properties which we are going to consider for our analysis? So the hardest case would be environment being partially observable, where you have a sensor data which is noisy and not complete. Multi-agent, competitive or cooperative multi-agents. Non-deterministic, which means that you have completely uncertainty, you cannot determine by the current state or the current action taken by the agent. And sequential, which means that you are going to have a long-term impact of current actions. Dynamic, which means that environment changes, it is not static. Continuous, which means that the sensor data what you receive is along the time, is continuous like time or space. And unknown, you don't know exactly what outcomes or outcome probabilities, what are the list of outcomes or the probabilities associated with those outcomes. If you don't know it, it becomes an unknown. This is the complex case which someone would like to solve. And the perfect example for this is the taxi driving case, where you are going to have the toughest case. There are other examples which comes under kind of slightly simpler, and so for example, like you take a chess, it is fully observable, multi-agent, deterministic, sequential, semi-dynamic and discrete. So all these examples falls into various levels of complexity, and we attempt to study a different case. I'll just list out what we are going to study. So give me 1 minute. Okay, so no problem, let's get back to the case whenever it comes. So yeah, let's now move to another concept. So let's recollect what we have discussed till now. We have seen what is an agent, what is an environment. We have discussed what is a rational agent, where it needs to have a performance measure, and we have came up with something called as a task environment, which contains PEAS, performance environment, actuators and sensors, and we have discussed various properties of environment. So now let us see how we are going to solve these problems whenever a particular agent falls into these various properties of various types of properties of environment. So as earlier said, agent function maps the percept sequences to the actions, and the one we actually implement is called as agent program, which lists the procedure to which maps the percept sequences to the agent actions. So in together we call both this program and the architecture. So the agent architecture is a machine or the hardware, you can say. It can be a robot, it can be a small device, anything. So agent architecture and agent program is together called as an agent, and we have 4 different kinds of agent programs: simplex, model, goal based and utility based agents. So simplex reflex agent is a simple logical, you could say, a if and then condition where you have so and so percept sequence, do so and so thing. Whereas the model based reflex agent are more based on experience of the past percepts, and thereby try to provide a better action for the current percept. Whereas goal based agents are purely based on reaching the goal. You have a initial state, you have a goal state, and you would like to reach to the goal state, and this is where the search and planning algorithms comes into picture. So we attempt to learn those search techniques as part of this reaching the goal from the initial state. And we also have a utility based agents where you have an utility function to quantify how good is this, and thereby usually we use expected utility, maximize expected utility, and attempt to reach the objective. So all these agents, especially the last 3, model, goal and utility based agents, are all learning agent. So here a lot of discussion goes on, but the mainly we would focus on goal based agent, where we say that we have a state, initial state, and a final destination state which we would like to go, and we would like to reach, find out the path which makes us to move from initial state to the destination state. And the algorithms which are involved in such movement are called as search algorithms, and that's what we are going to discuss in the next video.